One of the things we talked about in 9.1 was about boundedness. We talked about a sequence could be that a sequence could be bounded above or below or both. Specifically, we looked at the least upper bound or greatest lower bound, like we did this example here, where we wanted to show that this sequence was strictly increasing. So we used the derivative to do that. And then also we found the least upper bound, which was the same as the horizontal asymptote. Okay, so that's what we started with in 9.1. And then in 9.2, we revisited series. Okay, we revisited series where we were adding the terms together. We also talked about two specific types of series, the collapsing series, which is this one right here, and the geometric series. And in the case that either a collapsing series or a geometric series converges, then we're able to figure out what does it converge to. In other words, what we're asking is if we add up all of the terms in the infinite sequence, okay, so if we are able to add up an infinite number of terms and we get a finite number, like in this case, it was 1/3, okay, for this particular series. If we get a finite number, then that series converges, okay? If we do not get a finite number, in other words, if this limit doesn't exist, or if, in the case of geometric series, we aren't satisfying the condition where the ratio is less than 1, then we have a divergent series, okay? And I mentioned at the time that one of our goals is going to be to find ways to identify whether or not a series converges, and we may not even be able to tell what it converges to. We just want to say for sure, yes, it does converge, or no, it doesn't converge. These two examples, collapsing series and geometric series, are two where we can figure out what it converges to, but that is not always the case, okay? Now, later down the road, we are going to look at how to determine, how to estimate or how to approximate what a series may converge to with, and we can even determine like what our possible amount of error is. But for now, we're going to look at several tests that will determine yes or no, does the series converge, but not necessarily what does it converge to. Okay, so that's what we're starting with in 9.3, and 9.3 and 4 are going to have several tests that we're really going to need to be careful about keeping straight the criteria for each one, because some of them are going to be very similar. So, and I know I talked about this last week, but be very precise with your terminology and your definitions that you are using with each of these, and make sure, like when we say integral test, you specifically are thinking of this test, okay? And obviously this is new, but as you become familiar with it, it's something that we need to know very well so that we can differentiate it from the other series. Okay, so primarily 9.3 is about the integral test. I do have another one listed here, and then there's one at the bottom. But so the bounded sum test right here, this just says that if we have a series of non-negative terms, okay, so 0 could be included, and then positive terms, it converges if and only if the partial sums are bounded above. So what that's really saying is, so we're talking about partial sums being bounded above. If we take the sum, the nth partial sum as n approaches infinity, and all of those are bounded, well then we know that the entire series is. The problem is figuring out what that sum is usually what we don't know how to do, okay? So even though it's listed here and it's listed in your book, you're really not going to do much with that, okay? But you have seen it, all right? If for some reason a series says, hey, all the partial sums are bounded above, then yes, you can say by the bounded sum test, then it converges. But this is not even one that's going to show up on the list of all the series that when we get to our summary in a couple of days. Okay, so let's talk about the integral test. If we have a series, okay, if we have a series, an infinite series of whatever a sub n is, it converges if and only if the integral from 1 to infinity of the function that's the same as the series. So remember, this is explicit, this is this is discrete, and this is continuous, okay? So if and only if the integral from 1 to infinity converges. Okay, now I will tell you that sometimes we are not limited by just 1 to infinity. Sometimes it's a little more restricted, like maybe we'll go from 2 to infinity or 5 to infinity, because between 0 or 1 and whatever that starting point is, maybe something else is happening. But the idea is if we go to infinity from some finite starting point, then if the integral converges, then the series converges, okay? And we have done plenty of improper integrals because this is what we did in 8.3, okay? With the integral test, we need to make sure we are checking for 3 conditions, okay? And you need to write when you're doing this, did you check the conditions? So is it continuous? Is it positive? And is it decreasing on either 1 to infinity or, whatever our domain is, okay? So after we have determined, yes, it's continuous, yes, it is positive, and yes, it is decreasing on the domain all the way to infinity, then we will evaluate the improper integral from 1 to infinity, or whatever the starting point here is, to infinity. And if the limit of the integral converges, then we can say, yes, this series converges, okay? And I've got another note here that says, look for series that appear to be easily integrable. What that means is if I'm looking at a series and I'm looking at the a sub n, the rule inside the summation, okay? And I say, hey, I bet I could take the integral of that pretty easily. That would mean that the integral test would be an appropriate test. If I have something that is inside here that I don't know how to integrate, so for example, factorials. We don't have a method for integrating factorials, okay? So if there's factorials in here, I'm not going to try and use the integral test. But so for now, obviously, all of these will be using the integral test because that's the section we're in. But as we build our list of different tests to use, then we're going to need some ways to distinguish what would be the most efficient or the most appropriate method for testing for convergence. So this is what we're looking for with the integral test, okay? All right, so let's go through a couple examples. So for this first one, we have the sum from 2 to infinity. Notice we're not starting at 1, of 1 over k times the quantity natural log of k squared. Does not matter that the index variable here is a k. All right, it could be an n, an I, a k, all of those are common. And the first thing we do is we check the conditions. So is this a positive and continuous and decreasing function if I write it as f of x? So like if f of x is 1 over x times natural log of x squared, is it continuous, positive, and decreasing on 2 to infinity? And the answer is yes, it is. But this also brings up a point about why we're starting at 2 and not at 1. If I would have started at 1, then my first term would be 1 over 1 times the natural log of 1 squared. And the natural log of 1 is, yes, I'm sure that you all just said 0. We can't have division by 0, so that's why we are starting at 2. Okay, so yes, 1 over x times natural log of x squared is continuous. So is it continuous? Yes. Is it positive? Yes. And is it decreasing? Decreasing. I know that this is decreasing because as k increases, k times the natural log of k squared gets bigger, okay? If my denominator gets bigger, then I have a decreasing fraction. So yes, I know that all 3 conditions are met. So since the conditions are met, now what I'm going to do is I'm going to apply this integral, okay? So, and because I know this is an improper integral where we're approaching infinity, I'm going to go ahead and put the limit as t approaches infinity in front of this. So we have the limit as t approaches infinity of the integral from 2 to t of 1 over x times the natural log of x squared dx. And it's a definite integral, so does it really matter if we use an x inside here instead of a k? No, it does not. However, I am using an x to say that I'm differentiating between the continuous function f of x and the discrete series f of k, or f of k in this case. So does it really make a huge difference what letter you use? No, it does not, but let's get in the habit of using this. Okay, so then we're going to evaluate this. I do see that I've got a natural log raised to the negative second power, okay, it's in the denominator squared. I also have the derivative of natural log of x present, so that tells me that I can use u substitution, and I'm going to go ahead and write it out here. So u is natural log x, du is 1 over x dx. Something that I think we may have forgotten a little bit in the last chapter Even if we're doing an improper integral, if I use u substitution, I need to change my limits to be in terms of the same variable as my new integral. So they need to be in terms of u as well. Okay, so this is equal to the limit as t approaches infinity of the integral from, now it's not from 2 to t anymore, it's going to be from, if I plug 2 in here, it's going to be from the natural log of 2 to the natural log of t, and then I'm going to have u to the negative second, and then the 1 over x dx is exactly equal to du, so I'm replacing that with du. Okay, now I can use the power rule, and I get the limit as t approaches infinity, and then the antiderivative of u to the negative second is going to be negative u to the negative first, evaluated from natural log 2 to natural log of t. And then using equal signs and correct notation throughout, because we're using complete statements, we then have the limit as t approaches infinity of, and I'm going to have negative 1 over natural log of t minus negative 1, so plus 1 over natural log of 2. And then last step is evaluating this limit at infinity. If I plug infinity into here, the limit of infinity is infinity. So negative 1 divided by infinity approaches 0. So I end up with 1 over natural log 2. Okay, what did that determine for us? Let's go back to our test. It says if the integral converges, then the series will converge as well. Because 1 over natural log 2 is a real number, we can say, yep, this series converges. Okay? Now, it does not converge to 1 over natural log 2. There's a distinction here. We did not find the sum of all of the terms from 2 to infinity of 1 over k times natural log of k squared. Okay? All we did was use this test to show that the series converges, okay? And by the way, I'm going to, if I haven't already by the time you're looking at this, post a link in Schoology to a page that gives you a very quick demonstration of why the integral test works, okay? So if you want that little bit of background, you can go back and look at it, but we're just not going to spend time on it right now, okay? All right, so let's try another one. I'm going to suggest that you pause right here and try the second one, and then when we either are stuck or have had time to come up with an answer, then hit play and watch the next one. For the next example, we're looking at the series 4i times e to the negative I squared. Keep in mind, e to the negative I squared can be written as 1 over e to the to the positive I squared. Okay, so the first thing we do is we check the three conditions. Is 4i times 1 over e to the I squared as a function, would that be continuous? Yes, it is continuous. Okay, is it positive? Yes, because e to a power can never be negative. Even if we're dividing by that, it's still positive. Okay, and then is it decreasing? Yes, because even though we have an I in our numerator, which means that the numerator is going to be getting larger, we're dividing by an exponential that's raised to a higher and higher power. So the limit at infinity would of 4i times e to the negative I squared is still going to go to 0 because the denominator is getting bigger much faster than the numerator. So yes, this is also a decreasing series. And by the way, when you're doing this, when you're using the integral test, you do not have to go through the process of proving that a series is decreasing. You do need to check it, because if it's not decreasing, we can't use this test. But so if you mentally look at it and say, yes, I understand that my denominator is getting bigger faster, so the quotient is getting smaller, then that's enough just to, to say, yes, I checked and it is decreasing. Okay, so because it meets the three conditions, then we can apply our integral. And notice I'm not using an equal sign here. That's not because I'm being lazy, but because this series is not equal to the limit of the improper integral. The improper integral is what I am evaluating in order to determine if this series converges, but they are not equivalent. Okay, so we have the limit as t approaches infinity of the integral, and we're starting at 1 this time, from 1 to, from 1 to t, of the function, I'm going to write it as f of x, of 4x times e to the negative x squared dx. So here, I might look at this and think, because I've got this polynomial piece and the exponential piece, that maybe I need to use integration by parts, but we do not need to. We again have a u substitution situation. We have a composition, and the derivative of the inside of the composition is present, or at least we can manipulate it to get that, okay? So I am going to write out the u substitution again. If you are very comfortable with integrating compositions by now, you do not have to do this as long as you are getting the correct answer. But if you are not, then I would strongly encourage you to continue to write out the u substitution. Okay, so looking at this, the inside of my composition is negative x squared. So u is negative x squared. So du is going to be negative 2x dx. Okay, do I have a negative 2x dx? No, I have a 4x, but I can factor a negative 2 out of this, and I can put the negative 2 in front of this, or I can move it to the front of the whole thing. It does not really matter. Okay, so now I have negative 2x times dx. That's my du, and then this is going to be e to the u. So I have that this is equal to negative 2 times the limit at infinity of the integral, and again, changing the limits to be in terms of u as well. So the limit from, or I'm sorry, the integral from negative 1 squared, so negative 1, to negative t squared of e to the u du. Okay, and then that we can evaluate. So we have, we have negative 2 times the limit at infinity of, and then the antiderivative of e to the u du is just e to the u. We're evaluating from negative 1 to negative t squared. As a reminder, when we are integrating with u substitution, we do not need to go back to being in terms of the original variable. Leave your limits in terms of u, leave your antiderivative in terms of u, okay? All right, and then that is equal to negative 2 times the limit, as t approaches infinity, of e to the negative t squared minus e to the negative first, okay? And then evaluating this limit, I get negative 2 times, and then e to the negative infinity squared, that's 1 over e to the t squared at infinity, which does approach 0. So I have 0 minus 1 over e, which is equal to negative 2 times negative 1 over e, so 2 over e. Okay, once again, we did not determine what the sum of this series is. We do not know what this series converges to. We do know that it converges, though, because this is a real number. So we can say, therefore, the series converges.